Let's dive into TikTok's ad click prediction system and understand how 1% accuracy improvement equals $100 million revenue.
TikTok serves ads to over 1 billion users, generating billions in revenue. A 1% improvement in ad click prediction accuracy can translate to hundreds of millions of dollars in additional revenue. To achieve this, TikTok needs to make millions of predictions per second with a latency budget under 100 milliseconds. Here's what 90% of ML engineers get wrong when designing such a system. By the end of this video, you'll know exactly how to build a scalable, real-time ad click prediction system and how that 1% accuracy improvement translates to real dollars in increased RPM, revenue per milli. How do we measure success? Offline, we use metrics like AUC, log loss, and NDCG to evaluate ranking quality. But these aren't enough. Online, we track CTR and revenue per milli, RPM, to measure actual business impact. We also need guardrail metrics like ad diversity and user engagement to prevent negative side effects. Calibration is critical because we need well-calibrated probabilities for accurate bidding, not just a good ranking. A model with high AUC but poor calibration can lead to wasted ad spend. Your interviewer is testing whether you understand this nuance. Calibration ensures that a predicted 0.8 probability of click actually translates to 80 clicks out of 100 impressions. We use Platt scaling and isotonic regression to calibrate the probabilities. Let's look at the high-level architecture. Think of this as two pipelines working in concert, a prediction pipeline and a data pipeline. The prediction pipeline handles real-time ad serving. A user request hits the load balancer, then the API gateway. The request flows through a three-stage model cascade: candidate generation, ranking, and calibration. The data pipeline handles feature engineering and model training. User interactions flow into Kafka, then split into online and batch paths. Online features are computed in real time and stored in the feature store. Batch features are computed offline using Spark and stored in the same feature store. The feature store acts as the bridge between the online serving and offline training. Latency is key. We aim for 50 millimeters end-to-end. The API gateway adds 5 millimeters, feature fetch from feature store 10 millimeters, inference 20 millimeters, and overhead, API calls logging, adds another 15 millimeters. We use an A/B testing framework to compare model performance and monitoring to track key metrics. If the feature store fails, we fall back to default features. Remember the 1% accuracy lift we discussed? This architecture is how we achieve it. We use Redis as an embedding cache to reduce latency because it provides fast key value lookups with sub-millisecond latency. We also have a fallback mechanism to handle failures, ensuring system resilience. Where does the data come from? Primarily user activity logs, as ad impressions, and conversions. These are ingested into Kafka for real-time processing. We use a feature store like Feast to manage both batch and real-time features. The feature store is like a restaurant prep kitchen, ingredients pre-chopped and ready so the chef, model, can work fast. A major challenge is the cold start problem. How do we handle new users or ads with no historical data? For new users, we rely on demographic data and contextual information. For new ads, we can use content-based features and transfer learning from similar ads. Data quality is also critical. We continuously monitor for feature drift and missing values to ensure model accuracy. Your interviewer might ask, what happens if the feature store is down? We fall back to a set of default, hand-engineered features. This ensures the system remains functional, albeit with reduced accuracy. We chose Feast because it supports both batch and real-time feature serving, unlike some older feature stores that only handle batch. An experienced interviewer will probe, why not use a simpler key value store instead of a full-fledged feature store? The answer is that Feast provides versioning, transformation, and feature lineage, which are crucial for model reproducibility and debugging. Feast also supports point-in-time correctness, ensuring consistent feature values for training and inference. What features do we use? We can categorize them into user features, ad features, and context features. User features include demographics, interests, and interaction history. Ad features include category, creative content, and advertiser information. Context features include time, device, and location. Feature crosses are critical for CTR prediction. For example, user or interest etc. Ad category captures the interaction between a user's interest and the ad's category. Since we have many high cardinality categorical features, We use feature hashing to reduce dimensionality and handle unseen values. Feature drift is a constant concern in production. We monitor the distribution of each feature over time and retrain the model when significant drift is detected. This helps maintain model accuracy in the face of evolving user behavior. We use feature hashing instead of one-hot encoding because it's more memory efficient for high cardinality features. Your interviewer will push back here. Why not use embeddings for categorical features? The answer is that embeddings require training and can be slow to update, while feature hashing is a simple, fast, and memory-efficient alternative. Feature hashing uses a hash function like murmur hash to map features to a fixed size vector. Let's talk models. We start with a baseline, logistic regression with handcrafted features. This gives us a quick and dirty initial model. For candidate generation, we use a two-tower model. The two-tower model is like speed dating. Quick compatibility check first, deep conversation, ranking, only for top matches. We have a user tower and an ad tower, each generating embeddings. This allows us to pre-compute embeddings offline, which significantly reduces latency. Then we select the top K candidates, say 100, for ranking. For final ranking, we use a deep neural network or a transformer. This model considers feature crosses and nonlinear interactions to predict the click probability. Finally, we apply a calibration layer using Platt scaling or isotonic regression to ensure well-calibrated probabilities. Remember, we need accurate probabilities for bidding, not just ranking. An interviewer will ask, why a two-tower model instead of a single deep model? The answer is latency. Two-tower lets us pre-compute embeddings offline, while a cross-network requires real-time inference for every pair. We use Platt scaling because it's a simple and effective method for calibrating probabilities, especially when the model is miscalibrated. Isotonic regression is another option, but it can be more prone to overfitting. Platt scaling maps the output of the model to a probability distribution using a sigmoid function. Position bias is a major issue in CTR prediction. Ads at the top get more clicks, regardless of relevance. To correct for this, we use inverse propensity weighting or include position features in the model. We also need to address exploration versus exploitation. We use multi-arm bandit strategies like epsilon greedy or Thompson sampling to discover new high-performing ads. Think of exploration like trying new restaurants. You might find a hidden gem. Exploration matters because user preferences change over time and new ads are constantly being introduced. Without exploration, we'd be stuck showing the same ads repeatedly, leading to decreased engagement. We use Thompson sampling because it balances exploration and exploitation more effectively than epsilon greedy. Thompson sampling works by maintaining a probability distribution over the expected reward for each ad, allowing for more informed exploration. Epsilon greedy, on the other hand, explores randomly with a fixed probability. Our training pipeline uses distributed training with Horvath to handle large data sets. Negative sampling is crucial due to class imbalance. We use importance sampling to select negative examples that are more likely to be clicked. This improves training efficiency. Temporal distribution shift is a major challenge. User behavior evolves over time, so we need to continuously retrain the model. We use a model refresh cadence that balances accuracy and cost. We evaluate offline using AUC and calibration curves on held-out data. Before full rollout, we use A/B testing in shadow mode to compare the new model with the existing one. Your interviewer will probe, why not just use random negative sampling for class imbalance? Because random sampling ignores the fact that some negative examples are more informative than others. Importance sampling focuses on those harder negatives. Importance sampling assigns higher weights to negative examples that are more likely to be confused with positive examples, leading to faster convergence and better model performance. Horvath is used because it simplifies distributed training across multiple GPUs or machines. For serving, we use TensorFlow serving or torch serve. We use an embedding cache like Redis to store pre-computed user and ad embeddings. This significantly reduces latency. Let's break down the latency budget. Feature fetch from the feature store takes 10 MLOps. Inference takes 20 MLOps. And overhead, API calls, logging, adds another 20 MLOps for a total of 50 MLOps. If the cache misses, we fall back to a heuristic model. We use model versioning with gradual rollout and canary deployment to ensure safe updates. Cost optimization is also important. We balance batch and real-time inference based on traffic patterns. Remember the 100 milliamps latency target? This is how we hit it. We use TensorFlow serving because it's a mature and scalable serving framework with built-in support for model versioning and A/B testing. TorchServe is another option, offering similar capabilities with a focus on PyTorch models. We monitor key metrics like CTR, revenue, latency, P50, P99, and model calibration drift. We set up alerts for drops in CTR, latency spikes, and model staleness. Feature drift detection is also crucial. We monitor the distribution of features over time and retrain the model when significant drift is detected. This helps maintain model accuracy. Model decay is inevitable, so we continuously monitor performance and retrain when necessary. We use tools like Prometheus and Grafana for monitoring and visualization. A common issue is noisy data, which can lead to inaccurate metrics. Beyond performance, we need to consider fairness and ethics. We need to avoid ad targeting that discriminates against certain groups. We also need to comply with regulations like GDPR and CCPA, which restrict data usage. Handling traffic spikes like those during Black Friday requires careful capacity planning. Finally, we need to be mindful of cost. Large-scale inference can be expensive, so we need to optimize our infrastructure and model size. Remember that 1% accuracy lift we discussed in the beginning? Ethical considerations and fairness contribute to long-term user trust and engagement, which ultimately impacts that bottom line. We can use techniques like differential privacy to protect user data and ensure fairness. Differential privacy adds noise to the data to protect individual privacy while still allowing for accurate analysis. Let's recap. We designed a system with candidate generation, ranking, and calibration. Position bias, calibration, and feature crosses are critical components. We balance accuracy, latency, and cost. If I had more time, I would explore multitask learning to predict clicks and conversions jointly. Remember the 1% accuracy lift? This system is how you get there, translating to millions in revenue.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.